Hello, my name is Adish Merling, and today I'd like to talk about Enceladus. Last recording I made going over this took about 20 minutes, which is a little bit over the 10-minute time frame we were given. So I'm going to try to keep this one brief, go over everything I'm talking about as fast as I can, while still giving you the relevant information. So we're going to be going over Enceladus under the view of speculative ecology and biology, which was the study, or was the focus of my review paper. So let's get into it. As we all know, Enceladus has these massive geysers at the South Pole that are shooting out ice particles and water, which have been detected by Cassini and by many other instruments over time. And this leads us to believe that there is a subsurface ocean that is being heated by tidal flexing. Now, what tidal flexing is it's basically, you can imagine it like this. As Enceladus gets closer to Saturn in its orbit, it gets stretched out because the force of gravity being exerted on it from Saturn gets larger the closer it gets, according to Kepler's, I can't remember which law, but according to one of Kepler's laws. So it stretches out, and then as it gets further away, it compresses back again, and this stretching and compression leads to heavy friction, which produces a lot of heat within the core and within the rest of the materials around it. This heat forms a gradient, with the heat inside wanting to come outside towards the cold water and the cold ice shell, which leads to hydrothermal and geothermal energy, or geothermal sources of energy. We have evidence of this in silica that has been detected inside the plumes. Silica is basically sand, can be produced in high temperatures and high pressures, both of which are conducive to geothermal activity, which tells us that there is some sort of geothermal, hydrothermal activity going on beneath the surface. This would in turn cause a chemical gradient in which chemicals are produced by the hydrothermal vents, which escape into the water, and this gradient itself can be used by hypothetical life forms. Furthermore, as water heats up, it actually escapes in the plumes of Enceladus that we know of. These plumes eject into the E-ring of Saturn, and we're not sure yet if they come back. But if they do, and they become deposited on the surface, glacial movement, glacial tectonics, can bring that material back down into the water. We don't have any evidence of this on Enceladus specifically, but we have evidence of it on Europa, and the surface terrain of Europa and Enceladus are quite similar, especially in the places where it's very new ice. So we have that going for it. So let's talk about what's really difficult about living in a sea that has ostensibly no energy, no sunlight, no heat being formed, or barely any, at least. So the first question is, of course, where do we get energy without direct sunlight? On Earth, photosynthesis drives our ecosystem primarily with light being turned into sugar in combination with water by plants. So how would a moon and an ocean that has basically no sunlight actually produce the energy needed for life to exist? Furthermore, is it going to be the right temperature for life? We know that there's a very hot core and a very cold ice shell. So would there be a place in between those in which life could hypothetically exist as we know it? Keep in mind, this is including extremophiles. We want to ensure that we don't make any assumptions about the life that lives there based on our own sort of predispositions to Earth life. The life on this moon may very well be extremely adapted to extreme environments. And last but not least, can nutrients come back after being ejected? We discussed this in the last slide. It's a difficult question. There isn't much research done on it yet, but if there is tectonic activity or glacial tectonic activity movement from the ice shell, we can assume to some extent that nutrients may be coming back into the water. So these next two slides are going to be something of a double whammy. They sort of explain the heat and the energy questions of the previous slide. So first of all, hydrothermal vents, what are they? Basically, when a large amount of heat, in this case magma, starts warming water that's in the porous rock, that rock starts heating up, wants to go up due to the heat gradient produced, and it becomes what's known as evolved seawater. Basically, this means that it's been heated enough that it starts reacting with the minerals and rocks around it, which form a lot of chemicals that are very important to life and very important to the basis of an ecology. Then colder seawater comes into the same place where that warm water was, and it causes a loop of water coming in, evolving, getting shot out. So As you can see in this diagram, the plumes contain helium, iron, manganese, all really good stuff, but we're going to be focusing on these last three. These are the really important ones because these are seen a lot in organic chemistry. That being methane, CH4, carbon dioxide, CO2, and sulfite ions, that being H2S. So these are used can be metabolized by life as we know it. We've seen evidence of this on Earth. And furthermore, the heat produced by these vents could indeed create water temperatures that are conducive to life as we know it. Another way that heat can be produced, other than magma, is through a process known as serpentinization, in which water touches a very specific type of rock and then reacts with it in a highly exothermic reaction, which again can produce heat that may be allowing life to survive inside. But it also generates, among other things, hydrogen and carbonate. So hydrogen is going to be really important when we talk about methanogens, but the carbonate actually can react with the hydrogen, produce methane, which again is a very important part of anaerobic metabolism that we'll talk about soon. These then come up, they get ejected in their own sort of plumes, and this would be an alternative way that we get hydrothermal vents. So now that we have our answers to heat and energy, let's start talking about the possible metabolisms that might evolve and allow an ecosystem to start evolving on in an ocean like this. So these are what I like to call the first-hand harvesters, methanotrophs and sulfur oxidizers. Methanotroph literally means methane eater, as is shown in this highly elaborate left-hand diagram here. You don't have to understand everything that's going on, but what you should understand is that the methane is coming in, it reacts with proteins and enzymes and such, and produces amino acids, fatty acids, sugars, and nucleotides. So all four basic monomers that we see in cellular life that are necessary to maintain functioning inside an organism. Also, I said monomer earlier. It's polymer. I'm not making that mistake. So methanotrophs especially are going to utilize, or could utilize, what's known as a clathrate. Clathrates you can imagine as a sort of cage of ice being formed around a gas. In this case, methane, as is shown in these two images. They're found in the deep sea on Earth, and basically what happens is methane gets trapped in the ice and then gets stored there for an indefinite amount of time. Looks just like ice, but if you were to take a match to it, it would start to burn, as is shown on the right image. Clathrates can form around any sort of like gas or soluble material, but methane clathrates may be a very important part of an environment on Enceladus. So these clathrates could be tapped into by methanotrophs, or the methanotrophs could simply live inside the plumes and gain energy that way, albeit they'd have to be very developed to high temperature, high acidity environments. Sulfur oxidizers can also do the job. They take the sulfide ions that are being produced, they oxidize them, turn them into biosulfur, which can then be turned into sulfates, which will be important to sulfur reducing organisms. Keep in mind, this sulfur oxidization in the image here is aerobic, so it requires oxygen, which isn't great news because Enceladus, we have no signs that Enceladus has a very oxygen-rich water environment. But if there is oxygen being produced there, then we may see sulfur oxidizers in around these vents. So as these organisms start producing all this energy, taking the energy that's coming out of the vents and storing it in the form of sugars and fats, we can assume that they'll start to grow and eventually die off. And that brings us to the second-hand harvesters. So as this decomposing material sort of starts spreading throughout the water, either gets brought up by plumes and spread throughout the ocean, or is just drifted off by ocean currents, we may see these things get decomposed by fermenting organisms and methanogens. So fermenters are what allow milk to spoil and beer to be created. They're plentiful on Earth, and they're great because they are an anaerobic process. They don't need oxygen. So they'll take organic material, break it down into hydrogen and carbon dioxide, which just so happen to be the two primary cuisines of methanogens, which will then take the hydrogen and the carbon dioxide, they turn it into methane, amongst other things, which is important because then they'll be cycling another nutrient back into the environment. They're producing methane that can then be in turn used by methanotrophs. So we're building a cycling system here, which is very important to the basis of an ecosystem. So this is the dreaded part of the presentation where I try to explain this very complicated diagram I've made here. But I'll try to do my best, and I'll try to keep it quick. So down here at the bottom, we have the hydrothermal vent. This one's being caused by magmatization, or is heated by magma, whereas over here we have serpentinization, which is the water-rock interaction. Methane is produced, gets fed into the methanotrophs, who are going to be living nearby these vents, who will turn it into sugar and fats, increasing the energy density of the areas sort of around these vents. I'll draw those in there. We also have sulfur oxidizers and reducers who are going to be living in close proximity to each other, which will also boost the amount of energy that's being stored around these vents, which can be picked up by decomposers and detritivores, who will turn that material back into its constituent parts and cycle them back into the environment. Methanogens living near serpentinizing systems will also produce methane, and the serpentinization will produce methane itself, which again will feed the methanotrophs. Methanotrophs are going to get a lot of nutrients in an environment like this if we understand Enceladus' subsurface ecosystem to be like this, or subsurface environment to be like this. As the plumes rise, many of them will get shot out in these jets that we've detected on Enceladus. Nutrients may be involved inside these plumes. We haven't had instrumentation to detect those specifically yet, but we could in the near future. If these come back down and get deposited on the surface, nutrients may get dragged back down by glacial movement. Second of all, if these plumes are rising, they could get in contact with the ice and form clathrates if the pressure is high enough. And then glacial drift may actually push and pull these clathrates away from the plumes into a low nutrient environment where methanotrophs and sulfur oxidizers may actually tap into them, allowing these organisms to survive far away from the plumes, far away from a source of energy. These guys are going to have a hard time to live because they're basically living on a dying system. There isn't going to be enough clathrate forever because they're going to use it all up and there isn't a plume to steadily fill it. But it could be an interesting place to look for adaptations to this, like mobility, for example. If we have organisms that are going to try and get closer to the plumes, get closer to clathrates that are closer to the plumes, or we could see basic sort of multicellular activity where low energy living organisms actually get fed by higher density living organisms who pump sugars to them, pump energy to them, and allow them to survive even if they aren't in the best spot. I believe that this would be a great environment to search for multicellular and mobile forms of life if we were to actually get underneath the surface at some point. So there are my citations. Thank you very much for listening. I've cut it down to 13 minutes, still over the 10-minute mark, but I'm hoping that's good enough. You have any questions, let me know in class. I will be very happy to talk about them, and I'll be very happy to answer any questions even outside of class because Enceladus is like my favorite moon of all time. So thank you for listening, and I'll see you around.